Okay, so let's keep going with chapter 5. And now we're going to sort of define the ideal gas law. So from the previous slide, we saw the empirical gas laws. We know that volume, volume varies in proportion to pressure and temperature and moles. So Boyle's law says that volume is indirectly related to pressure. Charles' law says that volume and temperature are directly related. And then Avogadro's law says that volume and the number of moles is directly related. So if we put all that, there is some kind of proportionality constant that will govern all these relationships. So what we end up with is this. We say, okay, volume is directly related to moles, which is N, T, which is temperature, and inversely related to P, which is pressure. And so there's some constant that relates all of these, and they call it R. R is called the proportionality constant, referred to often as the ideal gas constant. So it turns out if you were to confine it by using standard temperature, because we know volume, we know that R, if R using a volume, the volume is 2.4, we know that 1 mole. Liters, 1 mole state pressure is when the surface temperature is 273 Kelvin, so that in, we can find the value of R is 0.0821, and these are 100 liters and moles times Kelvin, so we'll put on the denominator. Of course, this is where we use we're using units, so to be able to cancel all the units out. This number you should remember 0.21 liters per ton. Okay, so this gives us the gas law, gas equation, then we say EV equals RT is made up of this over. Yeah, remember when you like gas law makes some of the other laws because have ask here to cancel out the constant R. Volume has to be in liters, and because of atoms, it be moles, we can cancel moles. R for the universal constant is 100 per Kelvin. And then George always has to be 10. So this is a nice last variable of previous narration. Using that, we would have the N if we knew the D and B. That probably didn't show thread. All right, so here's an example. An experiment calls for 3.5 moles of chlorine gas. What volume should we measure if the gas is at 34 degrees Celsius and 2.4 atmospheres, 2.45 atmospheres? So we can rearrange our equation. PV equals nRT, V equals nRT over P. We know N is 3.5. We know R, 0.0821. We know T, but convert it to Kelvin, to 307 Kelvin. And we know P, and we have all our correct units. The moles will cancel. The moles from R will cancel. The Kelvin will cancel, and the ATM will cancel. And so the only units left over will be liters. And so our volume is 36 liters. All right, in chapter 3, we showed the relationship between moles and mass. Moles equal mass over molecular mass or molar mass or molecular weight, however you want to call it. Because again, molecular weight is moles per grams per mole. Molecular weight is grams per mole, and so moles is grams divided by grams per mole. So moles is mass divided by molecular mass. So little n for moles is equal to the mass of the sample divided by the molecular mass or molar mass or molecular weight, however you want to look at it. But that's comes from molecular mass or molar mass. Of course, that's the molecular weight from the periodic table. So if we substitute into the ideal gas equation, we can do that. PV equals little m over big MM RT. And if we rearrange this equation, you can actually solve for molecular mass. And so you could do this in different steps, but if you remember this equation, you could solve a problem that is looking for the molar mass of something by taking the mass of the sample times RT divided by PV. So you might want to remember this equation, or you might, if you just remember molecular weight is grams per mole, then you could do it in 2 steps. So let's look at an example here. A 15.5 gram sample of an unknown gas has a volume of 5.75 liters at 25 degrees Celsius and pressure of 1.08 atmospheres. What is its molecular mass? So we know that's our equation. We know the grams is 15.5. We know R, 0.0821. We know T, 25 degrees plus 273 is 298. And then we know P is 1.08 atmospheres and V is 5.75 liters. So you plug those numbers in. All your units should cancel. Atmospheres cancel, liters cancel, Kelvin. You'll end up with the units of grams divided by moles. So our unknown gas has a molecular weight of 61.1 grams per mole. We can also take this equation and rearrange it again a little bit. If we multiply both sides by molecular weight, mm, and then divide both sides by V, we're going to end up with density. Mass over volume is density. And then now density then equals P times molecular weight divided by RT. So it's another, just another variation on this equation. All right, so calculate the density of ozone, whose molecular weight is 48 grams per mole, at 50 degrees Celsius and 1.75 atmosphere. I've given you some easy ones. Don't forget that if your pressure is not in atmospheres, you need to convert it to atmospheres. So take the torr or millimeters of mercury divided by 760 will give you atmospheres. All right, so density is P mm over RT, so that is equal to 1.75 atmospheres times 48 grams per mole divided by 0.0821 liters atmospheres mole Kelvin divided by 323 Kelvin. The Kelvin will cancel, the moles will cancel, the atmospheres will cancel, and you'll end up with grams per liter. So the density is 3.17 grams per liter. So all of these equations are very helpful. You could probably, figure them out just using PV equals nRT. If you knew grams and volume, you could figure out density. But these equations are handy and already rearranged for you. All right. So one other thing that we need to consider is stoichiometry. And you may remember, again, from chapter 3, that always when we convert in a balanced chemical equation, we have to use the mole-to-mole ratio. So in chapter 3, we started with grams and we converted to moles. And then we were able to, say grams to moles of our reactant, and then we could convert from moles to moles of what we were looking for, and then moles to grams of our product. And then actually in chapter 4, we did the same thing, but we converted from liters using molarity. You could convert from liters to moles by using molarity. And then again, the mole-to-mole ratio is critical to get from one product in a balanced equation to another. And then you could convert back to liters using molarity. Well, Here's one more thing that we can use. Now we know how to solve for moles using PVE. If we know the pressure, volume, of course we know R, and temperature, we can find moles. So if we know the moles of one compound in a balanced equation, we can find the moles of another compound by using our mole-to-mole ratio. Okay, so look at this example. This is a reaction. KCl3 will react to give us KCl plus oxygen. So KClO3 is for chlorate, I think, or potassium chlorate. And so this is a balanced equation. So let's suppose we heated 0.010 moles of potassium chlorate in a test tube. How many liters of oxygen would be produced at 298 K and 102 atmosphere? So let's think about this. We know how many moles of potassium chlorate we have, but we're looking for how many liters of oxygen. Well, we know our volume, temperature, and pressure. So moles, let's see, we don't know liters. We know pressure and temperature, and we're looking for liters. If somehow we could also find the moles of oxygen, then we would be able to find the liters because we know PV equals nRT. Well, we do know how to do this problem because if we know the moles of KClO3, we can find the moles of O2. So let's look at that. Okay, so if we have 0.010 moles of KClO3, there's 3 moles of O2 produced for every 2 moles of KClO3 that are reacted. And so this means we'll produce about 1.5 times as much, 0.0150 moles of O2. So now we're good because if we know the moles of O2, we can plug it in the ideal gas law. So now we know that volume equals nRT over P. We know N is 0.0150 moles of O2. We know R, of course. T is 298 Kelvin. That was in the original problem. And the original pressure in the problem was 1.02 atmospheres. So if we solve this, moles cancel, atmospheres cancel, Kelvin cancels, and we'll end up with liters. So 0.360 liters of oxygen will be produced at this temperature and pressure. So here's another example, and this is really important in the industrial world because let's say you are a manufacturer of cars and you need to figure out how to inflate an airbag. Now, it turns out that this is the reaction to Na3 sodium azide. When it's hit, it will decompose into two sodium metal, 2 of them, plus 3 nitrogen gas. It's the nitrogen gas, again, that blows up. But it's really important that your airbag blows up to the correct size. What if you don't have enough sodium azide in there to produce enough nitrogen to blow up your balloon? Or what if you have too much in there and there's too much nitrogen and it explodes the air balloon airbag? It's not going to be any use to you. So you want to have the correct amount of sodium azide. So again, we need to use our mole-to-mole ratio that we can see in this equation to figure it out. So an airbag has a volume of 36 liters, so that's the volume we need. We want it completely filled with nitrogen gas, and we want it to have a pressure of 1.15 atmospheres and the temperature of 26 degrees Celsius. All right, so the question is, how many grams of NaN3 must decompose to fill the airbag completely? So if we think about it, what do we know? We know the volume, we know the pressure, and we know the temperature. So we can figure out how many moles of nitrogen need to be provided to fill up the airbag. Once we know the moles of nitrogen, we can convert moles of nitrogen to moles of NaN3, and then we can convert that to grams. So it's a two-step problem. The first thing we have to do is use PV equals nRT to find how many moles of nitrogen need to fill the airbag. So the number of moles is PV over RT. Again, you can see everything cancels except moles, and so we need 1.69 moles of nitrogen gas to fill up the airbag. So now we can use that 1.69 moles of nitrogen will 3 moles of nitrogen are produced for every 2 moles of NaN3, so 2/3 of the 1.69 will give us, let me see, will give us 1.13 moles of N2. And then if we multiply that by the molecular weight of NaN3, 65 grams per mole, we get 73 grams. 73.2 grams need to be put in there, and then they will produce the correct amount of nitrogen to fill up the bag. Okay, so take some time to think about those problems. They're fairly straightforward. Usually you're given all the information that you need. Okay, Dalton's law of partial pressure. The sum of all the pressures of the different gases in a mixture equal the total pressure of the mixture. All right, what does that mean? So if I have a bunch of different gases mixed together in one container, the total pressure will be just the pressure due to the first gas plus the pressure due to the second gas plus the pressure due to the third gas, etc. If we look at this picture, it'll make a little bit more sense. On the left-hand side, you see that flask A has just helium, 152 millimeters of mercury. And then on flask B has 608 millimeters of mercury of hydrogen gas. So what they're going to do before mixing, they each have their own pressure, 608, 152. Then what they do is they add the oil to flask A, which pushes all of the gases from flask A into flask B. And so now flask A is completely empty, and they've mixed the two gases together, and the total pressure in flask B now is the sum of the individual partial pressures. Okay, so you can always find out what the pressure of one gas is by knowing the total pressure and the pressures of the other gas. It's a similar thing in our atmosphere. Each individual gas has a partial pressure. All together, they form the pressure of the atmosphere. All right, so we can actually use this to calculate how much of something there is. Sometimes we use something called a mole fraction. A mole fraction, which is given the symbol X, is just the number of moles of one component divided by the total number of moles. So you can see here, like if you had a bunch of different gases, gas A plus B plus C, the mole fraction of A would be the number of moles of A divided by the total number of moles of A plus B plus C. It's also equal to the pressure of just A divided by the total pressure. So in that previous example, if we wanted to know what was the mole fraction of helium, it would be 158 divided by 780 or 760, the partial pressure of 1 divided by the total pressure. So if you rearrange that equation, the partial pressure of one gas is just equal to the mole fraction of that gas times the total pressure. So we can always find out what is the partial pressure of any gas just by knowing its mole fraction. And each gas can be treated independently. So if we just wanted to know what's the pressure of gas A in that system, the pressure of A will be equal to is in the relationship PV equals nRT, would just be the moles of A. So we can look at one simple example. We have a mixture of gases in the atmosphere, and the total at standard pressure, the atmosphere is 760 torr. What will the partial pressure of nitrogen be if the mole fraction of nitrogen is 0.7808 at 25 degrees Celsius? That's not really important in this problem because they're just telling you what the mole fraction is at that temperature. We know that the partial pressure of any gas is equal to its mole fraction times the total pressure. So in this case, we just take the mole fraction, 0.7808, times the pressure, 760 torr, and we find out that the partial pressure just due to nitrogen is 593 torr. Okay, that's the end of the second segment of chapter 5. There's one more video to go.